yield lines, special cases. This video will deal with square slabs with a partial distributed load, and the edges are simply supported. So we have here a slab simply supported with a dimension of A, and the load is equal to Q times B squared, and B is between 0, of course, and A. When B is A, the slab is fully loaded. Find the yield lines. We will now look first at the location of the axis of rotation, which is on the supports. We have 4 supports, you have 4 axes of rotation. When those axes are crossed, or at the cross points of those axes, we can draw the yield lines. So it's one there and one here. Under unit deflection in the center of the slab, we will see that on the edge, the deflection is 0. In the middle, it's delta, the unit deflection, and the otherwise it's 0. And the angle of rotation is theta. We assume that there is a small angle of rotation, so it means that the tangents of theta is almost equal to theta when expressed in radians. When we take this right-hand side, again, deflection is 0, deflection there is delta. Then we can see that theta, for small thetas, it is equal to delta divided by A over 2. And delta 1 divided by this distance here is also the tangents of theta. So this is the tangents of theta, this is the tangents of theta. And out of this, we can see what delta 1 is. It's a very simple relation between them. And delta m is then this part which has a uniform deflection of delta 1. So this is delta 1, plus you have this little triangle with the length of this side equal to delta minus delta 1. And because it's a triangle, so it's 1/3. So that's the delta m. And delta m can then be simplified to this expression. So bear in mind, delta m is the mean deflection of this portion of the slab, which is loaded. So this does not count, which is loaded. And when assuming that in the center, the deflection is delta, and on this side, it's 0. The work done by the external forces is then always the summation or the integral of the vertical load times the displacement. So this means for us, it is a total load Q times B squared multiplied by the mean value of the deflection. So in fact, it is 4 times this part that we already calculated. So that's why it's QB squared. And delta M from the previous slides, we know this is equal to this expression, and that's the expression for E. The work done by the internal loads is then, of course, the integral or the summation of the plastic bending moments projected to the axis of rotation, which is LE, times the angle of rotation. So D is equal to 4 times because we have this yield line projected to this axis, and then we have that 4 times. So D is equal to 4 times the plastic bending moment times the L, which is the projected projection of the yield lines to the rotation of axis, which is A. And the angle of rotation is, of course, delta divided by the maximum distance, which is A over 2. So D is equal to HM delta. Now, by making E and D equal, we calculate M. And this is the expression for the maximum bending moment in this slab. This is a general formula. We will now consider when the slab is fully loaded. So B is equal to A. And then we see that the maximum bending moment is Q8 squared over 24. So we find again the already known maximum bending moment of a square slab uniformly with a uniform distributed load. Now let's consider a rectangular slab with point support E in the center. We know that from the general equation of the previous slides for the uniform distributed load, it is this expression. We say P is the total load is equal to QB squared, total load. So M is P over 24 and so on. And now B is equal to 0, then, or the limit, you take the limit. So the limit is 3P over 24 or P over 8. So it's a point load divided by 8. Now we can formulate the general formula in a different manner. And we will use the load ratio, which is beta, and it equals B over A. So beta is 1 when the slab is completely loaded, and beta is 0 or very small, let's put it this way, when there is a point load only in the center of the slab. So we rewrite this equation by substitution, and we find in this equation the Q8 squared over 24, which is which we recognize as the maximum bending moment for a slab totally loaded over the whole surface. What is left is a function which we call k of beta, and k of beta is equal to this. We can put this into a graph, and then we see for beta from point load to fully loaded, we have the different values of k beta, and the bending moment is then very easily calculated as the bending moment caused by fully loading of the slab multiplied by this factor k beta.